Okay. As was just said, I'll be talking about the paper that I wrote on flexible barometric tactile sensors for robotic grasping applications. I'm Aiden Shaevitz. I'm in a robotics lab at Oregon State in the United States. So I want to start by talking a little bit about what a barometric tactile sensor is to begin with. Um, Basically, what these are is a set or singular MEMS barometer that gets cast or encapsulated in a body of some sort of silicone or other soft material. And then when loads are applied to that body, it distributes them to the MEMS barometers. And this is then interpreted as a pressure reading corresponding to your load. Now, the MEMS barometer has been um, around for a little bit over a decade now, with some of the originals starting to show up around 2013, 2014. And I hadn't really seen a lot of use, but there's a lot of really attractive things about them as sensors. Um, they're very inexpensive to make. They're also very, very easy to reconfigure and design, both electrically and in terms of just mechanical design for integration with systems. Uh, Very easy to fabricate in lab without a lot of expertise or expensive equipment. And they also have this nice element of added compliance. A lot of times in robotic grasping, especially when handling delicate objects, we like to have some degree of kind of cushion to offset for any kind of um, uh, inconsistency or lack of precision in our control. So barometric tactile sensors, you see them used a bit more recently in a lot of pretty common robotic um, grasping applications, things like contact localization, object recognition. You see them used in slip detection tasks. Um, and then, as I mentioned, there's this added component of um, compliance that gets introduced into your system. We see this used in things like uh, soft fruit harvesting, apples, berries, etc. But one of the things that we noticed with these, the current state of these sensors was they were all on these rigid substrates, these traditional PCBs, and we wanted to make them more accessible for use across a broader range of robotic grippers, both those that just naturally have some degree of non-flat or rigid geometries, switching to wanting to make them usable with either curved or flexible grippers, especially with growing interest in soft robotic graspers. And what we've done here is fairly simple. We've gone from a commercially manufactured rigid PCB to a commercially manufactured flex PCB. Not particularly revolutionary, but the simplicity of the transition allows us to keep pretty much the same manufacturing process as before, but with the added benefit of the flexibility. So again, using this flexible this PCB, we can now mount these to curved surfaces and deformable grippers. Um, as I mentioned, these are pretty easy to fabricate. The primary reason being that you're going to have some sort of commercial PCB manufacturer do most of the work for you once you've done the design. So from the commercial manufacturer, you're going to get your flexible PCB. We use stiffeners on these across the entire body, not just in selected locations, so that we can try to prevent any kind of damage during mounting around any kind of mechanical fasteners. And then the user, you can optionally do any of your component soldering if you're doing in-house, or you could have your manufacturer do that. And then really all that you have to do is the silicone casting process, which is very, very simple to do. So assuming that you've gone ahead and soldered your components onto this PCB, you're doing a very light amount of surface preparation, either with just a small amount of sanding. You could conceivably also do some sort of chemical process if you wanted a really, really smooth surface prep. Not smooth, I suppose. You want it roughed for the next step, being to apply a silicone epoxy We use silpoxy for those familiar, and this is done for the next step, which is to help bond the surface of the flexible PCB to the silicone that gets poured. So using a basic 3D printed mold, the PCB gets placed inside the mold. You pour the silicone in before the silicone epoxy is cured, and then they kind of co-cure. And you end up with a very nice bond between your silicone and your PCB, with relatively like good peel resistance around the edges. Now, because we've used these sensors a fair bit before, um, we have a pretty solid idea of the kind of behavior that we would expect to see out of them should they be functioning properly. So we went ahead and did a fairly simple sensor characterization just to kind of evaluate whether that's operating similarly to what we've seen before. So to go about doing this using a Mark 10 just materials tester, uh, we mounted the sensor just in this 3D printed jig with this long just steel kind of indenter, measuring force and displacement with a load cell mounted on the materials tester. Both are sampled at 20 hertz just for convenience sake. But starting with the probe at the surface of the sensor, fairly basic, lowering 2.5 millimeters, keeping it static for 3 seconds, and then raising back to an unloaded state. So here's the results from that experiment. Basically, on the left here, we have the pressure in red in millibar as reported by the barometers on the tactile sensor. This is a gauge or a differential pressure based off of the unloaded atmospheric readings. So not an absolute pressure, you're removing the atmospheric pressure readings from that. So only the load. On the right, we have the load cell force, and then this is all relative to the displacement. And we did a couple experiments. One is with the indenter directly centered over the barometer. So over the silicone, over the barometer, and did the experiment as I just described. And what we see is that the pressure response is very much in line with what we would expect given the loading from the materials tester. So that's nice. No strange behavior. Silicone can often introduce kind of odd behaviors, undesirable behaviors into tactile sensors. One of which being hysteresis, which in this case we see almost none of, if any at all, which is quite nice. The viscoelastic effects of silicone can often be very disruptive to capturing more real time, and then also understanding like what's happening on the release portion of a tactile signal. Now, the next was some loading that we did with the indenter centered over the edge of the silicone, so at a distance from the actual MEMS barometer on the tactile sensors. Note that the pressure scale on the left is now operating is now displaying the negative. This is because as you load, we actually see an inverse relationship between the actual load cell force and the perceived pressure or contact force at the barometers. We speculate this is just due to actual material being kind of pulled up and away from the actual measurement point in the barometer. This is something that we also see in primarily shear loading cases. Typically, this is something that you would probably want to avoid, but can potentially be useful given certain circumstances, as long as you're aware that it can happen. Now, being that we're interested in doing or designing this for robotic grasping applications, we went ahead and mounted it to a robotic gripper, although it's ironically more of a manual gripper. It is a manually activated kind of simulated version of a robotic gripper, just for testing sake. And so we have two of them here on these curved fingers, grasping a 10 centimeter diameter 3D printed cylinder. Um, we didn't have anything in particular that we were interested in necessarily identifying about its behavior here, except just verifying that its behavior is consistent with a tactile sensor that's grasping a cylinder. And so what we see here is in the regions where we see this variable Nmax is kind of mechanically, you would intuit this is the regions with the highest normal force loading, given that it's most normal to the surface of the cylinder. And we also see that in this plot here, which basically is just showing if I were to grasp actuate, because I'm the one actuating this, over a period of time and then releasing slowly, the highest signals are the ones that are also labeled as the Nmax. So we do get some verification that there is a difference in pressure readings that is in line with what we'd expect. Then we also see some of these negative pressure readings that were common more so in the barometers closest to the base of the gripper, where you're not getting very much normal loading, but primarily shear loading along the surface. So just to briefly summarize, this flexible barometric tactile sensor is a rather direct and simple kind of transition from a more traditional rigid version of these barometric tactile sensors. And so they kind of retain a lot of these nice properties, being really easy to design, very easy to fabricate, and remain relatively inexpensive. This makes them a pretty attractive option in robotics, where we're aiming oftentimes for rapid development and deployment to test a broad set of systems and not necessarily just tactile sensors. Thank you.